Okay, good afternoon everyone. Welcome to SME Design Workshop. So let me introduce our demonstrator pretty quickly. My name is Chai. I am a final year ECSE and ComSci student. We also have Alan over there who is doing ECSE as well in his third year. We have Tim over here doing ECSE and ComSci. And finally we have Cameron over here, third year ECSE as well. Cool. So this is the first workshop, and this workshop we will go over the theory behind how the sensor actually works, and gonna end up introducing you guys to KiCad, which is our choice of the design software. The second workshop, which will be happening next week Friday same time, we will guide you through the final schematic design as well as the complete PCB design process. And finally, third week, which is in week 8, we will hopefully get to assemble your board and get them tested. Okay, so before we go into the actual content, I would like to ask everyone to download KiCad on their devices, just so that we can save some time setting it up later. It's fairly simple. You can just Google KiCad download or go to this link over here, and just choose your operating system and download it. Let's just give like 1 or 2 minutes for everyone to download that. And if you have any questions, feel free to ask as well. Okay, so all right, let's get right into it. So what is a soil moisture anyway? A soil moisture sensor anyway? As you might have guessed from the name, it's just a sensor that we use to measure the moisture of the soil. And this is useful because, for example, it can tell us the optimal time to water our plant, which can avoid problems like overwatering and underwatering. And there are a lot of different types of soil moisture sensor. Some are more suitable for industrial purposes, while some are used in electronic hobbies. But there are two main types that are relevant to us. The first type is called the resistive or conductive sensor, which has two uninsulated prongs, as shown in the top image here, and it works by measuring the conductivity between those two prongs. So if we stick the sensor into a soil, the soil will act as a variable resistor because wet soil has to tend to have higher water content. It makes it more conductive than dry soil and therefore less resistive. So using that sensor, we can determine how wet or dry the soil is by simply measuring the resistance value, or more accurately, the voltage drop between the varying resistor. This is very simple, and the actual sensor itself is quite cheap, but it has a major flaw in that those exposed prongs corrode very easily after only a few usage, meaning that we would have to replace the sensor quite frequently. The second type is called the capacitive sensor, and this sensor has a single prong and it is insulated, usually done through epoxy coating or in this case solder masking. So how this sensor actually works is quite interesting, but just a general overview, it measures the dielectric permittivity of the surrounding environment, which in our case would be the soil, and we can determine if the soil is wet and dry just from that. The good thing about the sensor is that it has no exposed electrodes, meaning that we can use it for a very long time without damaging it. And that's why we have chosen to build this capacitive one for our project. Okay, before we go into the sensor itself, I want to give you guys a quick refresher on what a capacitor is. Since everyone here is mostly second years, I assume everyone knows what a capacitor is, but simply put, it's just a passive component that stores energy in electric field between two plates. For a simple parallel plate capacitor, like the one in the image, we can easily determine its capacitance, which is just the ability of the capacitor to store charges using the surface area of the plates and the gap between those two plates, as well as what we call the absolute permittivity, which is just the product of the constant vacuum permittivity and the relative permittivity, which is unique to the environment of the capacitor. So that means a capacitor in open air might have different capacitance than when it is submerged in water. And this is the foundational concept that we are going to use in our sensor to determine if the soil is wet or dry. Okay, so just to warm things up a bit, I want you guys to quickly calculate the capacitance value of a capacitor in different environments, given that we know its surface area as well as the plate's gap and the environment's permittivity are shown in that table. Let's spend like 1 to 2 minutes working on this problem quickly. Meanwhile, if you have any questions, feel free to ask any of us. Okay, sorry. Okay, cool. So hopefully everyone has done that. Let's go over the solution quickly. Using the parallel plate capacitance formula and the given values, we can get the base capacitance expression. which only depends on the relative permittivity, which is this one. And then using the relative permittivity values from our table earlier, we can get these three values for each of the environment. This question is hopefully everyone get that same answer. Let me know if you guys got different ones. But this question is pretty trivial, but I put it here just to prove you guys that if we put the capacitor in the soil, a wet soil would give rise to a lot more capacitance compared to dry soil. Now we know the relationship between soil moisture and capacitance. What we want to do next is to learn how to actually capture the capacitor value, or more accurately, how we can capture the capacitor voltage value. To better understand how we can capture the voltage value, we need to look back at a fundamental circuit, which I know you guys are familiar with, which is the ECSE circuit, also known as the low-pass filter circuit. It's a very simple circuit with a voltage source and a resistor and a capacitor. And one of the most important characteristics of this circuit is its time constant, which determines how fast the capacitor charges or discharges. The time constant is also very easy to calculate, as it's just the product of the resistor and the capacitor value. Now, what would happen to the relationship between the capacitor and the time constant if we have a fixed resistor value? The time constant would be purely dependent on the capacitor value, right? To be more precise, the time constant is directly proportional to the capacitor value, meaning that if we have a big capacitor, it would take longer to charge or discharge compared to having a smaller capacitor. And this relationship can be seen in the graph to the right here, with the curve indicating the voltage of two capacitors being charged over time. The blue curve represents the smaller capacitor, and the red curve representing a bigger capacitor. As you can see, after 2 milliseconds, the smaller capacitor reaches around 9 volts compared to 6 volts for the bigger capacitor. So from this alone, we can conclude that just by looking at the capacitor voltage after a certain period, we can determine if the soil is wet or dry. Because remember, a capacitor in a dry soil has lower capacitance compared to in wet soil. Oh, sorry. Right. Sorry. So, right. But there's another way to look at this ECSE circuit. And in my opinion, it's a more interesting way and allows us to determine how to best design our circuit. As you might already know, capacitor has a property called reactant, which opposes alternating current. We can say that it is a resistive behavior of the capacitor when there's an AC input. And this reactant is inversely proportional to the input frequency and the capacitor value. That basically means if our input frequency or capacitive are high, the capacitor would be less reactant and would let the input signal pass through very easily. That's the characteristic of the capacitor with AC input. Now, what would happen if the input frequency is fixed? Then the reactant would purely be dependent on the capacitance, right? And for an ECSE circuit like this one with AC input, this circuit can sort of be seen as a voltage divider circuit, because we essentially have an input signal and one resistor and a capacitor acting like a resistor due to its resistive nature. So if we have a voltage divider circuit with fixed R value, then the output voltage, which is the capacitor voltage, would change depending on the capacitor's reactant and ultimately depending on the capacitor value itself. To be specific, based on the formula of the voltage divider at the bottom, as the capacitor value increase, the output voltage would decrease due to the fact that the capacitor's reactant would decrease as well. Now we have reached the same conclusion as before, right? We say that different capacitor value determines different output voltage after a certain period. So from this, we can once again conclude that the capacitor in dry soil would output a higher voltage value compared to the same capacitor that is in wet soil. Because remember, once again, dry soil has a smaller capacitance compared to wet soil. The next question to ask is how much of a difference in voltage is the dry soil compared to wet soil? And how can we actually maximize the dynamic range? That is, we want to be able to clearly separate the voltage reading between when it is in dry soil and it is in wet soil. In order to do this, we have to look at another property of an ECSE circuit. This property is called the cutoff frequency, denoted by FC. which is just the frequency at which the circuit starts to significantly attenuate the signal in power, meaning that it would lower the output voltage value. And for the RC circuit, which is just a low-pass filter, any input signal with frequency higher than this cutoff value would be severely attenuated. We can numerically determine the cutoff frequency of the RC circuit using that orange formula, and as you can see, it's inversely proportional to the value of the resistor and the capacitor. The graph on the right shows the relationship between the output voltage and the frequency of the RC circuit. If the input frequency is above the FC, so that means it's to the right of FC, then the output, to the left of FC, then that means the output frequency would be approximately to the input frequency, which is also the maximum frequency. Whereas if the input frequency is higher than FC, then the output frequency would be severely attenuated. So in this case, we can attenuate the input, the signal by changing the input frequency alone. But remember that in our case, the capacitor is the one that is changing, and due to moisture. So this would make our cutoff frequency the varying component instead of our input frequency, which also means we have the freedom to choose our a fixed input frequency, but we also have to choose wisely because we want to maximize the dynamic range between dry soil and wet soil voltage reading. In order to do this, we have to ask ourselves, what input frequency value should we choose to increase the range between the output voltage of dry soil and wet soil? Can anyone guess? All right. Remember, the dry soil has lower capacitance, which is supposed to have a higher output voltage. So we want to avoid attenuating the input signal when the soil is dry. Whereas wet soil has high capacitance, which is supposed to have lower output voltage. So we want to attenuate the input signal a lot. The answer is that the input frequency should be close to the cutoff frequency when the soil is in dry condition. Why does it have to be when the soil is dry? Well, if we look at this sort of animation, I cannot seem to find my slides. Sorry. Oh. Yeah, so for example, if we have the input frequency F0, FO, the orange line, and we have the cutoff frequency of FC, right now the input frequency is less than the cutoff frequency, which is to the left, which means when it is in dry soil, we would get the maximum output voltage, right? Because it is less attenuated. But as the soil gets wetter and wetter, the cutoff frequency would decrease by a lot. Decrease, and to a point, the cutoff frequency would decrease so much that it passes the input frequency, which is fixed. And we see that now the output voltage would be severely attenuated. Okay, cool. Oh, thank you. But we don't want to make the input frequency way too high or way too low as well, because this would only minimize our dynamic range. So the input frequency should ideally sit a bit lower than the cutoff frequency of the RC circuit in dry condition. Okay, so now let's do another quick calculations for the input frequency. From our research, we know that for dry soil, it has a capacitance of around 50 picofarad, which is very small. And if we have chosen the resistor to be 10K, what should our input frequency be? I've also attached a reference of the cutoff frequency formula for your reference, but let's just spend 1 to 2 minutes calculating this input frequency. Okay, so let's go over the solution quickly. We know that in order to maximize the sensitivity of the sensor, the cutoff frequency should be close to the input frequency, the point where the sensor actually swings the most between attenuation and complete pass-through. Since we have the resistor and capacitor value, we can easily calculate the cutoff frequency, and we just need our input frequency to be a bit above this. So our calculated cutoff is 320K, and we want to sit a bit below this, so around 300k hertz. Now we have determined the input frequency, but how can we actually generate this input signal? That's where a timer comes in, specifically the 555 timer, which you guys might have been familiar with if you guys have done 1013. The 555 timer can be used to create precise oscillation continuously in one of its modes, which is called the stable mode. And we are going to use the output of this timer to be as the input of our Aussie circuit. But how does this timer actually work, and how can we set up our input frequency? It's actually very simple, because we just need 2 resistors and 1 capacitor. This might look familiar to you because it's just another Aussie circuit. The timer itself has 8 pins which work together with an internal logic of the circuit to restrict the charging and discharging voltage of the capacitor to be between 2/3 and 1/3 of the input voltage. And when the capacitor voltage is at 2/3 of the input, an internal flip-flop would latch and trigger the output voltage high to match the input voltage. And this would also trigger the discharging phase of the capacitor until the voltage dropped back down to 1/3 of the input. Then the flip-flop would trigger the output voltage low, pulling the output voltage to be 0. And it also triggered the charging phase of the capacitor. And this cycle basically repeats continuously. If you look at the bottom figure, the green graph is the charging and discharging of the capacitor voltage, and the blue graph is the output voltage of our timer. When the capacitor is charging, the output voltage is pulled to its maximum, which is the input voltage, and when the capacitor is discharging, the output voltage is pulled low back down to 0. And since this is just an Aussie circuit with the combination of R1, R2, and C, then we can change the duration of the charging and discharging by simply by messing with the time constant values. And by changing the time constants, we effectively can change the frequency and duty cycle of the output. And this can be formulated through these 2 expressions. This formula can also be found in any 555 timer datasheet as well. And for anyone who is interested in learning about the internal working of the timer as well as the math breakdown, you can check out this website over here, which is outline a detailed working and explanation of the timer's logic. Alright, okay, so let's jump into another quick activity to calculate, in this case, the R2 and C value. We have the target frequency of around 300k hertz, and we want the duty cycle of the timer to be roughly 50.11%. And we have picked a fixed value of our R1 to be 1k. From this information alone, how can we determine the values of R2 and the capacitor? Let's spend like 2 or 3 minutes working on this problem as well. And I've also attached the formulas for the frequency and the duty cycle over there as reference. Okay, cool. Let's go over the calculation quickly. From the duty cycle formula, we can calculate R2 pretty easily, which we got to 220k. And from that, we can use the frequency formula to calculate the capacitance value as well, which we got to be 10 picofarad. Let me know if anyone got different values, but I think these looks correct. So even though our calculations are correct, if we look at our capacitance, it's very small. It's 10 picofarad. That is 10 to the power of -12. This is going to be a problem in real life, especially if you're designing PCB, which inherently would have something called stray capacitance or parasitic capacitance, which is just any unwanted capacitance that arise from traces on the PCB itself. And this stray capacitance is usually around 10 picofarad, which is the same as our calculated C value. This means if we were to use 10 picofarad, the actual value would be around 20 picofarad, for example, which would make our timer become very unreliable. So how can we counter this? Well, since our capacitor is small, what we want to do is make it a bit larger, right? Let's just do that. Let's pick a value of the capacitor to be much larger than 10 picofarad. And you can choose any value you want. Just make sure that it's quite significantly larger than 10 picofarad. So let's say if we picked a new value C to be 470p, and this is now a lot larger than our previous value. If we stick with our original R1 value of 1k, then our R2 value would be around 4.6k using our previous formula. And having that new R2 value, we need to check if our duty cycle is actually within an acceptable range. And we can easily do this using duty cycle formula once again, and we found it to be around 55%. Okay, so in the previous example, we let R1 be 1K, but you have the freedom to explore different combinations of R1, R2, and C value, and we highly encourage you to do this yourself, because from our experience of making this board, we have encountered multiple issues and we have to test out different combinations of values to find the sweet spot. But this is the reality between designing real circuits and ideal theoretical calculations. But we do have some recommendations. The first advice is to keep the operating frequency to be high, and the ideal range should be between 300 to 700 kHz. Just because that from what we know, higher frequencies tend to give more stable reading because it won't be affected by the salt and mineral of the soil. And we also don't want to go too high into the megahertz range because our timer can become very unstable. At the same time, we still want the cutoff frequency to be around the input frequency to be around the cutoff frequency when the soil is dry, which we assume to be 50 picofarad. In reality though, this capacitance value might be different for your board when you design it. If you want to be completely accurate, you would want to measure the capacitance of the board in dry soil condition, and you would use this as your basis for your calculations. And this can easily be done using the time constant formula. The second advice is to keep the duty cycle within 50% range. So somewhere between 45 and 55% is generally a good starting point. And lastly, we should aim to make the R2 to be greater than R1. This is purely because of what's known as the voltage divider effect, which I won't go into much detail, but essentially limits the current draw and also the voltage drop across the resistor. And one thing that we noticed from our board is that the actual frequency would tend to be lower than your calculated values as well. So that's something to keep in mind. And from our experiments, we have these values for R1, R2, C, and C value. And it tends to give us the most dynamic range of output, which is good because then we can easily separate our reading between wet soil and dry soil condition. Okay, so that was a lot of information, and it's not really interesting, it's boring. But let's do a quick recap of what we have concluded so far. Firstly, we say that a capacitor in dry soil would have less capacitance than in wet soil, and this affects the cutoff frequency of our RC circuit, which ultimately affect its output voltage. So we can use this information to say that if the output reading is close to the maximum voltage, then it's dry, and if the output voltage is very low, then the soil is wet. It's very simple. After that, we did some activities calculating the timer's operating frequency, which we say should ideally be a bit lower than the cutoff frequency in dry soil, since we want to maximize that dynamic range. And lastly, we also determined some component values of our timer. But there's one last problem, which is that our output value is still fluctuating. And if we were to read that output directly, then our data would be very messy, and it would be quite hard to interpret it. So what can we do to rectify the situation? Well, to do this, we can simply use a simple circuit called the peak detector circuit, which is just composed of a diode and another RC circuit. What this circuit does is it checks if the input voltage is higher than the output voltage, and this is done using the diode. If the input voltage is actually higher than the output, then the diode simply shorts, and the output voltage would instantly be pulled to have the same value as the input voltage. And the capacitor would start charging immediately. But when the input voltage falls below the output voltage, the diode essentially isolates the RC circuit, and the capacitor would start its discharging phase until the input voltage becomes larger than the output voltage once again, and the cycle would repeat. And if this cycle happened at a very fast frequency, and the discharging time of the capacitor is long enough, then the output voltage would become stable. And we know our frequency is fast enough because we chose the input frequency to be around 300 kHz. But how can we make our discharging time long? Well, we just need to make our time constant large. And if we set our time constant to be 1 second, which is long enough, then we can find the different combinations of R and C value using the time constant formula. In our case, we've picked the R value to be 1 mega ohms and the C value to be 1 microfarad. This is because making R large minimizes the overall current draw of the circuit. So from that, C value can be determined to be 1 microfarad given that the time constant is chosen to be 1 second. Okay, so now we have the complete picture of how of the circuit that makes the soil moisture sensor actually work. We have the 555 timer starting at the left, which produces a periodic square wave, which is then used as the input to our RC circuit. And since the capacitor of the RC circuit would change in capacitance, this would also change the RC circuit circuit output voltage. And to stabilize this output, we use the peak detector circuit. And finally, if we read the output of the RC circuit, of the peak detector circuit, we would be able to identify if the soil is actually wet or dry. Okay, so the next question you might ask is, how can we actually read this data? Once again, it's very simple. We'll just use an Arduino microcontroller, which you guys are familiar with already. It's easy to use. We can use it to power our board, our sensor, while more importantly, we can use it to interpret and read our data from the sensor. Okay, so moving on. So introduction to the more fun stuff of PCB design. We have already defined our schematics and determined our choice of reading the data. Now what we want to do is define some basic general requirements for our design. Since we will be interfacing our sensor with the Arduino, we want to be able to easily plug it and unplug it for debugging purposes. Also, we have chosen our operating voltage to be 3.3 volt, but you can choose to operate at different voltage as well, for example 5 volt. Just make sure that your components can withstand that. Another requirement is that our timer, which is the integrated circuit, should be able to handle high frequencies, around 300 kHz, and able to operate at 3.3 volt, or whatever voltage you have chosen. And we will go over how to actually check for these requirements later on. The next requirement is that our components should be fairly small and are through-holes components, because it will make our soldering job a lot easier. And finally, we want to be able to interpret our result. You can choose to detect the output voltage and just print the moisture value straight into your laptop terminal. But in our case, we have chosen to add a dual color LED, which flashes different color depending on whether the soil is wet or dry. Alright, so we have determined some basic requirements. Now let's go over how we can select good components. So what defines a good components anyway? This list is not exhaustive, but generally you want the components that is well documented and well tested. This would make any referencing and calculating a lot easier. Another important thing is to make sure that component is still in stock and not obsolete. Because imagine you finished your design in 1 week, but you have to wait for your components to arrive in like 12 weeks. And lastly, this is pretty much obvious, but it has to fit your technical requirements. This can include your operating requirements such as voltage and temperature, but also the physical requirements such as the sizing. Okay, so this is just a list of components that we will need. You don't need to remember any of this, it's just for referencing. But you may notice that the resistor and capacitor of the timer is highlighted. This is because you have the freedom to choose and test out different values and combination as before, but you can also use our values as well. And the LED indicator part is completely optional. Here we have the LED to indicate if the board is receiving power, and also another dual color LED to interpret our result. Again, this is not necessary, but it's considered good practice to at least have a power indicator LED on your board, and we will go over how we can calculate those resistor value later as well. Okay, so before we go off searching, there are a couple of steps that I recommend us following, as I found it to be helpful this way. First is to obviously define our requirements, and second, I would recommend using websites like Octopart, which is just a search engine for electronic parts, or you can just simply Google your search part, or another way is to go straight to the distributor websites such as DigiKeys and Mouser. Third one is that once you have searched for your components, there will be a lot of components that won't fit your requirements. What you will do is to filter out those components. Oh my days. Okay. And then after that, after you've found a couple of components that fit your requirement, what you want to do is to go through their data sheets. This step is really only necessary for core components such as our timer, because generally datasheets for passive components such as resistor and capacitor do not offer much besides their dimensions or footprints, as well as their tolerances, which would most likely be in the description anyway. Lastly, what you want to do is to check if your if your component actually have CAD integration or symbols that we can add to our PCB design software. Or you can find it on websites such as SnapEDA or Ultra Librarian as well. If they don't have, it's not the end of the world, because you can just draw up your own symbols in KiCad. Okay, now let's go find some components. What I want you guys to do is to go onto DigiKeys, search up DigiKeys. Oh wait, sorry. Before that, here's just a list of components of requirements that we would want to look for generally for passive components, such as their tolerances and max rating and footprint. This list is not restrictive. Generally, you don't really care about like the filming and stuff as well, but just for the sake of filtering, I've included that. Sorry. So let's go on to DigiKeys. So if you search, thank you. So if you just search DigiKey, I can't type. Okay, DigiKeys, it's this one, first link. And what I want you to do is search for a 10K ohms resistor. So what we want to do is 10K resistor. All right, so now we have a list of options. This is quite confusing, but remember that we want through-hole components. And if you look at this image, and the name, it's called through-hole resistors. If you just click on that, it would give us a list of components that are through-hole resistors and are usually 10K. Sorry. What we want to do next is to filter out those components, because now we have around 7K components. Some best practices is to filter out whether it is actually in stock, and we want to add data sheets as well as the CAD model as well. And as mentioned, we don't need to go through this, but also, what are some other requirements? We said tolerance should be 1%, and the max rating should be around 0.25 watt or 250 milliwatt as well. And metal film, 1% tolerance, and power rating of 0.25 watt. Cool. So now we have narrowed down from like 1,000 components to around like 73 only. Apply all. Cool. So now you can see that all these components would fit our requirements of 10K ohms, around plus or minus 1% tolerance, and fit our power rating as well. And if we click on one of the components, you would be able to find the same description, just for good measure, as well as their data sheets, which is here. Sorry. As you can see, like data sheets for passive components usually just have dimensions and package size and stuff like that, and generally just general testing. But so you don't really look at data sheets for passive components. But yeah, it's just for good practices, I guess. And you can also find the model of your components here, which you can download straight and import into your PCB design software, in this case, KiCad. Cool, that's just the general way of how we can go about searching for our components. Okay, so thank you so much. And this is just another list of requirements that we usually want. For example, the connector that we're going for is a 5-pin male header, which is the same standard as the one on the Arduino. But we won't go into much detail because it's just the same boring procedure that we did earlier. What I want to focus on is the timer selection, because there are a bunch of timers that won't fit our requirements, and it's also a good example to go over their datasheet as well. So we have defined earlier that the timer should be able to comfortably operate at around 300 kHz and at 3.3 volt, and it also have to be through holes, or in this case a what we call a dip package, so we can easily mount it on our PCB. Now what I want us to do is to go find some timers that fit this requirement or your own requirements if you define it to operate it at 5 volt, for example, or at a higher frequency. So once again, go on DigiKeys and type in 555 timer and try to find the one that actually fits your requirements. Let's spend around like 5 minutes looking at this, and if you have any questions, our demonstrator can guide you through it as well. Okay, so hopefully you guys have found some 555 timer that you guys actually like. So if you search 555 timer, it will give us some description as well. What we want to look for is the programmable timer and oscillator. Just click on that. Now it will the same give us just a bunch of timer that won't necessarily fit our requirement. And the same, just click on the in stock, has datasheet and CAD model as well. And what we want to filter out is that if you scroll to your right, you would see the mounting type here. Just click on through holes because that's what we want. And also I mentioned the 8 dip or P dip component as well. Just click on that and just apply. Okay, so now in this case we narrow it down to about 11 components that would fit our requirement. So just go over some of that. For example, this one, the LM555 or the TLC 555. Okay, so now we have chosen 3 components that would likely fit our requirements. If we go through it, the product description, for example, for this one, an E555, if we scroll down, we see that the voltage, recommended voltage is actually between 4.5 to 16 volt. Now, we said that our operating voltage should be at 3.3. So this timer actually does not fit our requirement. But if you have chosen your operating voltage to be 5 volt, it might. But 4.5 is actually cutting it close. So I wouldn't actually recommend this one. But if you look at another timer that we have chosen, this one is still 4.5. That does not fit our requirements. This one. Okay, so this one, TLC 555. This one has an operating voltage of from 2 to 15 volt. And it has a maximum frequency of 2.1 megahertz, which means it's able to operate at around 300K as well. So this is the likeliest components that we're going to use. If you look at its data sheets, open up the data sheets, what you would get is the first page usually features the descriptions, for example, the operating voltage as well, and they usually attach a package information because the same components can come in different packages. In this case, what we want is the P-dip, 8 pins, because we want it to be able to mount on our PCB. So in this case, we will use the TLC 555C with P-dip packages. Why? We know that if we scroll a bit further down, you would see a table of content that shows you a bunch of stuff. The most important thing about this datasheet is you would want to go to the recommended operating condition. You would see the manufacturer actually recommended to the supply voltage between 2 to 15 for this specific series alone. So even though it's the same timer for this one, it has the I series, which able to operate from 3 to 15, and this one, the M series, which requires 5 to 15. So you have to actually look for the TLC 555C version as well. And in the data sheets, another important thing is to go through is the detailed description, because the manufacturer usually outline how they want the circuit actually to be designed. For example, in this case, the functional mode would give you a detailed description of how you can assemble your circuit. For this case, we want to operate using the astable operation as well. Just this circuit, the same circuit, and also, as mentioned previously, the formula is here as well. So that's basically how we go about searching for the components. Okay, so the last thing that we will look at for our component is the capacitive probe itself, because we can't actually buy this component off the shelf, so we will need to design it in our software. But it's also not a simple parallel plate capacitor, as you might already know. It's called a coplanar or interdigital capacitor, which basically means it's the positive and negative plates exist on the same plane, and it works on relying heavily on the electric field to curve out or fringe out from one plate to another. You might have seen this if you've done engineering electromag. And since it relies on the fringing field, the capacitor is highly dependent on the environment, which is good for us. This is what we want. But the math behind this calculation is a bit complicated, so we won't go into much detail. However, it still has the base capacitance, meaning that the variable in the equations are fixed, and the only varying component is the relative permittivity. So our designs still hold because it only depends on the surrounding medium of the probe. And the easiest method for designing this probe is actually just to copy from the commercial one as closely as you can, because we would assume that they have tested their design thoroughly. Okay, so that was a lot of boring information about the theory part and component selection. Now we've ended the theoretical and component selection part. From here, we'll move on to the more interesting part of the workshop, which is the KiCad and schematic design, which I will pass on to Alan for that.
Hello. Hello everyone. I'm Alan, and for the second part of this workshop, we'll be basically getting into the meat and potatoes of actual PCB design. And what you all will do by the end of this workshop would have started the actual schematic for your sensor and would have downloaded and started everything. All right. So first of all, what even is a printed circuit board design, anyways? So this definition right here is taken straight off of Wikipedia, where a printed circuit board or a PCB is a laminated sandwich structure of conductive and insulating layers, each with a pattern of traces, planes, and other features etched from one or more sheets of copper. Now, in its most simple form, this is basically all PCBs are, right? All it is just you sandwich pressing a bunch of lines, copper lines together, and this forms basically the entirety of our electronics community or industry, right? For example, things like this NVIDIA GPU, right, has almost thousands, if not millions, of connections, tiny traces between all these layers, right? So, with that, such a simple premise can become very complicated, right? So, with this, how do we actually navigate between designing our boards? Well, luckily for all you, especially for you starting off, PCB design will be more of an art than a science, right? While you do need to know the equations and the technical knowledge, right, what you will find is that PCB design will also require you to be creative, right, and be practical. For example, if we look at these two boards right here, the one on the left both of these boards are electronically sound. They will work when you print them, but as you can see, the one on the left just looks a bit more messy, right? For example, if I told you to describe the layer of this board on the left, it would be a lot more difficult than the one on the right, mainly because this one's a lot more cleanly laid out. Does that kind of make sense? Yeah. So there are 5 steps into designing a PCB, right? For example, requirements, specification, schematic design, PCB design, simulation, and finally prototyping. So we've done the first part, we found all the components, we found all our requirements, and now we will actually get into designing our board. So firstly, what even is a KiCad or KiCad? This is a free and open source electronic design application, or an EDA, and essentially what it does is that it allows you to design electronics and convert them into physical PCBs. So the entire workflow involves what we said before, like schematic capture, drawing a logical design of the circuit, the PCB layout, define the board shape, as well as having a 3D renderer given to you, which is very useful, and as well as Gerber generation or the industry standard files. There are other softwares, like for example Altium or even Eagle, right? But the reason why we're using KiCad for today is because, well, not only is it free, it's easy to obtain and install. So, I just want to show of hands, how many of you have downloaded KiCad? Okay, who hasn't installed KiCad yet? Okay, can you please install KiCad, like as quick as you can? Just make sure, because what we're going to do very quickly is we're going to actually get into KiCad. Alright, so does everyone have KiCad open? Everyone?
Please.
Alright, cool. So what we're going to do is, where's KiCad? Is KiCad closed? So this is the project screen, right? Has everyone made a project, a blank project? Yep. It's basically, all you need to do is go to File and press it. File, new project, right? Find your place and then do it, okay? Alright, let's go. Alright, so first of all, now with KiCad, there are a bunch of there are a bunch of components which are built in. However, for our project, we need to import some custom components, right? Specifically two. So what I want you to do, just for now, I'll show you how to do it, and I'll keep this side up, well, after we do it. So first of all, we have preferences. So in order to import it, we go to Manage Symbol Libraries, right? You can see we have a bunch of these global libraries, and what I want you to do is I want you to download the zip file, which I will put back up, and then add the link to them, okay? So if we start by here, alright, right now you should have both of these imported, so once you press OK, it should do its magic. You do need to wait a bit. Alright, cool. So now let's get into the schematic, right? So let's get back to the slides. So first of all, this is the schematic editor. You don't need to worry too much about what every button does, but here are the main ones. So especially on the right, you place things, place whatever you want, right? On the top, you have your main functions, for example, rule checkers, assigning, footprint, and then PCB editors. On your left, you have your preferences. For example, if you want to add a grid, if you want to change like your angles or your sizes or your dimensions, and on your left, you have your properties, right? So firstly, what we're going to do is, how do we actually place things? I think I've already seen some of you place a few items. So first of all, you press the place symbols button, or you can just press A, right? So what we're going to do is, if we go back to KiCad, and then we press A, you have this giant, oh, sorry, I haven't. Why is it not switching?
You might have to drag it across.
Oh, here we go. Oh, it's loading. It's loading. 1 second. Cool. So, that didn't work. Cool. So something like this. So if you press A or here, you should open this menu, which is on my screen. That's so annoying. Why is it here? Can't drag it. So you have something like this, right? So this is your parts menu. You can see there are already a ton of parts, right? Now the first thing which I want you to look at is this device section, where it has basically all your generic components. For example, if you want a capacitor or a resistor, if you go down here, or you can even just search by pressing R, right? Resistor, variable resistor, blah, 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 right? We're going to use the RUS, right? Mainly because that's what the symbol that we learned in our units. So what we do, double click, and then we could place it wherever we want, right? So something like here. So does that make sense? So the second part, which I want to go through, is we have power symbols. For example, how do we place our 5 volt or our ground is basically by pressing this button. It's in a separate menu. So let's press P. Okay, so you can see power. If you want to add 3.3 volt, there's something right here. If you want to add your ground, there's one right here. So something like this. So I want you guys all to add a resistor and a ground. So by clicking this and double clicking it, what you can do is you can set the value, let's say, to 1K, right? Cool. So you can change your value like that, right? So the next thing we can do is, how do we connect each symbol to each other? Well, you can press W, or we can draw a wire, right? So simply, if we press this one right here, we can connect this ground, this lead to this ground, right? Now, I keep pressing escape. What we can do now is we can add a connector component, which I all want you to do, and it will be something like this. I want you to add. Wait, no, sorry. Connector generic. Where's connector generic? Yeah, so I want you to add this connector right here, and if you press X, you can also flip the component, and R to rotate it, and if you press W, we will add it, something like this. Voila. Is how do we add nets? So what is a net? Is literally a logical connection representing a set of pins or component terminals that are connected together. For example, on the one at the top, you can see those two nets are connected, right? Even if there is no wire. So why would we ever use nets instead of just connecting everything manually? It's because there will be situations where your circuit design or your schematic will be very messy, right? For example, if we want this wire to go all the way around here, that's probably not a good idea because it will be unreadable. So this is why we should add nets. So how do we add a net? We just press L, or we can press the button on the right, something like this. We can add a label property, let's say net, and then we put it here, right? So once we delete this line, right, we can place the net here. Oops, sorry, I can't press escape. Right, so something like that, right?
And what's the button for delete?
Sorry?
What was the button used to delete?
Delete. Yeah, you can also delete by pressing the delete key. Alright, moving on. Well, so the next part is, what do we do if something is not connected? Right? So what will happen if we have this connector, right? But we have 4 pins which aren't connected to anything, right? So the problem with KiCad or KiCad is that it will throw an error if something is not connected, mainly because it doesn't want any. It wants every single pin to be connected to another thing, right? Which is good for troubleshooting purposes. But what if we intend a pin to be set floating or set unconnected? Well, what we need to do is we need to add place no connect flags, or press it by pressing Q. All we need to do is press Q and add these 4 in here, right? 1, 2, 3, 4, right? So does that make sense? If you press Q on your keyboard or the X on the right toolbar. So I'll wait like 5 seconds. Okay. So that brings on to our first activity, our final activity of this workshop. And what I want you to do is I want you to make the LED circuit for our board. So essentially we have this 5-pin connector. You can arrange things as you want, right? All we need is 2 pins which are for the LEDs, and then 1 pin for ground and 1 pin for 3.3 volt, right? So we have our first LED, which is this one which we imported, which will be powered by your LED R and LED G. Now beware, one thing to think about is what voltage your LED R and LED G will be at. So that's one thing to think about. Your second LED will be powered by the 3.3 volt pin, and it will have the same specs as your red one. So that's your assumption. So remember, you need to add resistors, because you always need to add resistors to your LEDs. And if you don't know any of the specifications or whatever, I want you to check the data sheet. You have the model number, it will be the first link when you search it up. And I want you to calculate your resistances, all right? So get started.
Thank you everyone for coming to the workshop this week. That's all the content we have for you this week, but we have this room booked for a little bit of time after, so if you're stuck or still working on something, feel free to stick around. We have a QR code here on the slides. This will let you access the workshop materials that we have designed afterwards if you are working on things at home or if you want to go back over any of this. So I'll give you all a moment now to scan that and get access to the Google Drive. So next week in our workshop we will be covering finishing the schematic. So we'll be adding the capacitors, the timer, and the resistors. And then we will begin designing our PCB, placement of the components and routing them. So next week there should be a lot more practical stuff. We won't have to go over any more of the theory. Finally, thank you all for coming. Our next workshop will be run at the same time in the same room. So next Friday, the 27th at 2 till 4 p.m. in Menzies EG03. We, SME, run a lot of other events. We have a head of department forum where you can meet with Yan Wong and talk to him about the future of the ECSE department. So feel free to scan the QR code on the left to get tickets for that. And on the right we have our signaling panel, where we will be bringing in a panel of 4 people from the signaling industry, and you can pose questions to them and network with them after.
What about the undergrad teachers survey?
I don't know.